In this video, I want to talk about op-amps. I want to start explaining to you how op-amp works, and I want to start that by looking at what we call the ideal op-amp. Now, ideal op-amps are op-amps that function in a kind of idealized way, and all normal op-amps would deviate from this ideal behavior in some ways, but this is what we would want a very good or a very accurate or a very perfect op-amp to function like. Okay, it's a mathematical model, and many op-amps reach this ideal behavior in certain conditions. I think the importance of knowing something about ideal op amps is that we start understanding uh, op amps very easily by using these assumptions and by using this ideal behavior. And then we can add on the non idealities and the real kind of behavior and the deviations from this ideal behavior very easily around our basic understanding of the op amp. So so let me just draw an op-amp here. So we already saw that this is the symbol of a op-amp and that the op-amp has two inputs, what we call the non-inverting input and the inverting input. And let's just call this V in plus and V in minus. And the op-amp has an output. Let's call it VO. Now, the first thing I think that you need to know about the op-amp, and I'm talking about the ideal op-amp, is that the op-amp behaves as a differential amplifier. What do I mean by that? What I mean by that is that the op-amp takes the difference of the voltages at its two input terminals. Let's say that that difference is VD, and it amplifies it by a gain of AD. Okay, so VO is equal to AD times VD, which, okay, so it does not matter whether, so the only thing that matters for for deciding the output is the difference of the voltages between the non-inverting and the inverting inputs. So whether the voltage is 0 and 0.1 volts, or whether the voltage is 100 and 100.1 volts. In the ideal case, the output of both these inputs, for both these inputs, would be the same. Why? Because the difference here is 0.1 and the difference here is also 0.1. In addition, in the ideal op amp, we assume that this differential gain AD tends to infinity, which means that this differential gain is very, very high. And that is the first assumption in our ideal op amp model, or that's the first parameter of our ideal op amp model. So just repeating and summarizing, the first point that we said was that the op amp output can just be defined by the differential voltage, and this differential gain AD tends to infinity in an op amp. Now, of course, the question that you would ask is, uh, if you have a gain of infinity, wouldn't the op amp output be always infinite, right? So if you have a V in plus at the op amp, and if you have a V in minus given to the op amp, and this is the output, so depending upon which is greater, so let's say that V in plus is greater, then the difference here, the VD, is going to be positive. So positive multiplied by an infinite gain would make this output a positive infinity. If V in minus is greater, then what would happen? Then your differential voltage, which is VD, is going to be negative, and therefore VD times AD, which is infinity, would give you minus infinity as the output. And that is true, other than the fact that we have not accounted for the two power supplies, right? So let's call this V plus, the positive power supply, and let's call this V minus, the negative power supply. Now, in any op-amp, in fact, in almost any electronic devices, the output voltage cannot go beyond the power supplies, right? So what do I mean by that? What I mean by that is the maximum positive value of VO, or the output, is going to be V minus, and the maximum negative value of V output is going to be V minus. So yes, there is a gain, and the gain is infinite, but what happens is the output doesn't go to infinity, but it is stopped at V plus, and on the negative side it is stopped at V minus. Okay, and this phenomena where the output is kind of, it peaks at the power supplies, is called saturation. So saturation has happened when the output has reached the maximum value that is allowed by the power supply that is being given to the op-amp. Okay, so V, the output has to be in between V minus and V plus. Now what does it mean for the op-amp that we are talking about? Let's look at that in let me just redraw the op-amp circuit in another slide, and we'll come and take a look at that. Okay, so here's an op-amp, and we know that this is an ideal op-amp, and therefore the gain, the differential gain AD, tends to infinity, and the output only depends on the difference of the voltages VD, where of course VD is equal to V in plus minus V in minus. Okay, now and we are also saying that even though AD is infinite, V output is always bound, and the upper limit is V plus, sorry, the lower limit is V minus and the upper limit is V plus. So V output cannot go beyond this, and when V output reaches the lowest value possible, which is V minus, or the highest value, we say it has reached saturation. On this end, we call this negative saturation. Okay, and on the other end, we call it positive saturation. So this is positive saturation. So how would this circuit, which is shown on the screen, work? Now think about this. If the input voltages are such that VD is positive, what would happen? VD times infinity is positive infinity. The voltage cannot reach positive infinity but is capped by V plus, so the V output will be equal to V plus. If VD is negative, then negative infinity would be the output, but you cannot get any more negative value than V minus. So V output will be equal to V minus. Okay. One of the ways in which we can write this is by drawing a graph. So let's do that. And let's put V in on the x-axis, and let's put V out at the y-axis. Okay. And let's say this is our power supply V plus, and that's our value V minus. So that's on the negative side, and this is on the positive side. And similarly, V in positive and V in negative, that's 0. Okay, so now what happens? Whenever V in, okay, a mistake here. This is not supposed to be V in. I'm supposed to write VD here, right? Because the output only depends on the difference of the voltages, VD. It doesn't matter what V in plus or V in minus is. So the input is VD. So whenever we have VD less than 0, that is this part of the curve, what will be the output? the output is going to be V minus, right? Again, if Vd is negative, Vd times infinity is going to be minus infinity, but the output voltage cannot go more negative than V minus. So V output will be equal to V minus. So we have, so my output is going to be V minus whenever V in is negative. Oh, sorry, Vd is negative. Now what happens when Vd is positive, this side of the curve? When Vd is positive, following a similar logic, if Vd is positive, Vd times Ad, which is infinity, would be positive infinity. But the maximum positive value that we can reach is the positive saturation, which is V plus. So my voltage is going to be V plus. At the place where Vd is 0, 0 times infinity, well, that's a good question. We don't know. Maybe we could say that it's just going to be 0, and we'll leave it at that. Okay, so we have a circuit that gives you an output of V minus whenever the differential input Vd is negative, and it gives you a voltage of V plus whenever the voltage is positive, the differential voltage at the input is positive. Now this kind of a circuit is called a comparator circuit. And you can easily see why this is called a comparator circuit. It's called a comparator because it is comparing these two voltages that are being given at the input, right? So if V in plus is greater than V in minus, then our V output is going to be equal to V plus. If V in plus is less than V in minus, V output will be equal to V minus, right? And for the very simple reason that when V in plus is greater than V in minus, Vd is positive, and therefore we have this. And if not, we have this. And probably, if you want, you could talk about a third case where V in plus equal to V in minus, and at that point VO can be thought to be 0. So that's how a comparator works, and this circuit is basically a comparator. So there you go. You have one more block in your electronic tool kit pile, and this block is the comparator block. It can take two voltages and tell you which one is higher than the other.